Hi, everybody. Hope you guys are all staying well in your homes. Today's topic is plasmids, specifically talking about how we make those recombinant plasmids that we're putting into bacteria during artificial transformation, and how do we, what's called map a plasmid. So first things first, we talked about this a little bit already last time, but recombinant plasmids need a couple of things if they're going to be successful in artificial bacterial transformation. So one of those things that we didn't mention last time is they do need an origin of replication. Some kind of promoter region. If you remember DNA replication, we need a spot for DNA polymerase to be able to bind and actually start replicating the plasmid, so that every time the bacteria do mitosis/binary fission, they replicate themselves. We want the plasmid to be replicated in their progeny. Otherwise, it just exists in one bacteria, which is no good because they don't live very long. We also need a selectable marker. This is something we did talk about last time. So this is a gene that lets us select for the bacteria that actually took up the plasmid, and in like 90% of cases, maybe even more, that's going to be a gene for antibiotic resistance. So once we grow the bacteria on an antibiotic, only the ones that have taken our plasmid inside are going to be allowed to survive, and so we'll know that they were transformed. And then the other thing we didn't talk about that's super important is what's called a multiple cloning site. This is a place where multiple restriction enzymes can cut. That way we know that we can open the plasmid and actually insert our gene, and we can use many different restriction enzymes to be able to do that. So we're going to talk about how we know which restriction enzymes are able to cut that site next. Oh, and a little bit of bacterial transformation review. Now that you've done the lab, hopefully it makes a little bit of sense. You could go ahead and pause and try to answer these questions, or you can just listen in. So how do we get our gene of interest into a plasmid? Well, that's with restriction enzymes. We cut our gene, we cut our plasmid, and then by DNA base pairing rules, they're able to recombine together. Then, how do we get bacteria to actually take in the plasmid? Well, we have to shock them in some way with heat shock or chemical shock, like with CaCl2 you used in your virtual lab. And then, how do we know which bacteria actually took in the plasmid and successfully were transformed? Well, since the plasmid encodes a gene for antibiotic resistance, we'll simply grow the bacteria on an antibiotic, and only the ones that have the plasmid are going to be able to survive. Okay. So say we have a plasmid, usually we'll obtain plasmids from bacteria originally before we actually insert a gene. If we want to know which restriction enzymes are going to be able to cut the plasmid and where they cut, we're just going to run a few tests. So for example, we'll take this plasmid and cut it with an enzyme called EchoR1. Take a look at the plasmid. You can pause and think about it. Think about how many times does EchoR1 cut this plasmid, and how big of a piece of DNA is going to be left over if it does cut. So you can see here, EchoR1 only cuts one time, and so if it snips it once, this is a circular piece of DNA, we'll end up with just one fragment that's 20 kilobases big. So we would just see one line on a gel electrophoresis, for example. Now, if we separately cut this plasmid with BAMH1, well, that's going to cut at 3 sites. So you can go ahead and pause and see how big those pieces are going to be and how many pieces are going to be made. So this is going to be one piece here. That's going to be 2 kilobases big. We've got another piece here that's going to be 6 kilobases big. And then we've got this piece here. It's going to be 12 kilobases big. Hopefully that makes a little bit of sense. And we'd see each of those pieces of DNA come out in a gel electrophoresis, so we would know roughly what size that they were. And then finally what we would do is try to cut the plasmid with both enzymes together so that we can see how they connect. So hopefully you can see, I'm running out of time here, that EchoR1 is going to cut right in the middle of the BAMH1 12 kilobase fragment, so we'd end up with a piece that's 2, 6, 8, and 4. All right, and I'll pick it back up, the other example, in my next video.